correspond to the edges of the shadow zone. Since tag E1 is obscured and its previous tag E1-1 is not, the boundary line of the shadow zone can be defined such that it crosses their midpoint. Similarly, the other boundary line would be through point E2. Now we know 2 points that each boundary line goes through. The first is the antenna location, and the second is either point E1 and E2 respectively. So eventually the coefficients of each boundary line can be easily computed as demonstrated here. The boundary lines of the antenna shadow zone are nominally tangent to the target surface. The distance between each of them and the target center is a function of the coordinates of the circle center. Since the boundary lines are tangent to the circle, this distance should be equal to the circle's radius. Due to the absolute value operator, an ambiguity arises here regarding the correct sign value. As a result, 4 possible combinations of signs are derived, which lead to 4 different systems of equations. Each of the systems represents a different target solution that corresponds to a different quartile with respect to the antenna's position. In order to drop the absolute value operator, we will take into account the search area of the target and the fact that the antenna used is directional. The target center should be on the right of epsilon1 with respect to the antenna's position and on the left of the line epsilon2. Under such assumption, the correct sign value is chosen for each equation and the proper system is constructed that corresponds to the correct solution as well. The system contains 2 equations and 2 unknown parameters, namely the coordinates of the target center. On the Kalman algorithm. The step of the prediction uses a transition model which describes how the target is expected to move from time step t-1 to time step t. We have adopted a white noise acceleration model according to which the maneuvers of the target should be small and random and can be quantified by Gaussian distribution. The step of the update incorporates the collected measurements. At each time instant, measured phase samples are evaluated to form a 2x2 linear system, which outputs an estimation of the target's location. The measurement model H associates such measurement-based estimation with a dynamic state. In our case, we have implemented a 2-stage Kalman filter that consists of a forward and a backward filter. The forward filter is a typical one and starts from the first time instant and moves forward in time. The steps of prediction and update are repeated until the target exits the monitored area and the whole trajectory of the moving target has been constructed. After the termination of the algorithm, the backward filter is deployed to smoothen the estimated trajectory. It starts from the last time instant and moves backwards in time. The difference now is that all information, all measurements, past and future, are now available for its estimation. And as a result, it produces the best achievable accuracy. Here is an example of the improvement occurred by including a backward smoother in the method. The estimated trajectory of the target is depicted by blue dots. Notice that rough and fast changes of the trajectory have been removed, without, however, distorting the signal tendency. We have conducted experiments inside the multipath reach area. 25 passive UHF RFID tags were placed at 1 meter height, forming a gamma-like shape across the room. In the opposite side of the space, 4 patch antennas connected to the same reader were employed at a similar pace. During the experiments, a single human target is traveling at various speeds and trajectories through the enclosed space. The static locations of the antennas and tags, as well as the human's trajectory, were measured by employing Aruco markers. The camera-enabled laptop continuously monitors the area, and the obtained images are evaluated to estimate the position of the markers. During the experiments, the human carries an Aruco marker, and its locations are estimated by the camera in order to obtain the ground truth of the target. The experiments took place in 2 phases. During the offline phase, measurements were taken in a target-free space, and the average phase value and read rate of each antenna to tag pair were recorded. The online phase refers to the evaluation of the proposed method. During this step, a single human target moves spontaneously across the space, holding an Aruco marker facing the camera of the laptop. Here are shown the results for 3 of the experiments where the target moved across 2 gamma-like paths and 1 arbitrary. Green color depicts the trajectory derived by the camera system. Blue color represents the path estimated by the forward Kalman filter, and the red color corresponds to the eventual trajectory after the deployment of the backward Kalman's movement. Notice how well the smooth trajectory coincides with the actual one. As for the execution time of the algorithm, this plot shows compares the execution time with the duration of the experiment. The method contains no time-consuming operations, since the estimation is derived by solving just linear systems. This effect supports the real-time capability of the method. The cylindrical model enables localization even by a single antenna. The resulted estimation is shown in the first plot, where the result, although is not optimal, it is still quite satisfactory for realistic applications. By increasing the number of antennas, the estimation is gradually improved, where the trajectory derived by all 4 antennas best matches the ground truth. This plot indicates that localization error slightly decreases with the increase of the antennas. The median accuracy is improved to 15 centimeters when all 4 available antennas are taken into account. Next, we examine the considered radius of the cylindrical target. The middle plot shows the results for the optimum value of radius, and therefore the estimated trajectory, depicted by red, best matches the actual one, depicted by green. On the other hand, a much larger radius produces locations that are far away from the antennas, while a much smaller radius, such as 16 centimeters, produces locations that are quite close to the antenna. This figure shows the achieved accuracy for different values of radius. Best accuracy is achieved for a value around 24 to 26 centimeters, reporting a median accuracy of about 15 centimeters. An experiment of a gamma-like path was repeated for 3 different working speeds, labeled as low, medium, and fast. As we can see, the method still preserves its robustness for all speeds, reporting equivalent accuracy with a median error around 15 centimeters again, while no error greater than 40 centimeters was observed, even for the fastest speed. To conclude, we have presented the device-free tracking scheme that tracks a single human target by exploiting a cylindrical human model and phase disturbances of RFID tags. The shadow zone of the antenna can directly reflect the exact target location, while localization can be achieved even when a single antenna is available. Experimental results report a median error of slightly less than 20 centimeters, while the computational cost of the algorithm is negligible. As a future work, we'll focus on the extension of the method to multi-target scenarios in order to deal with more realistic applications. We have already tested clustering algorithms to identify multiple shadow zones of the same antenna that correspond to different targets. That was all. Thank you for your time.
So thank you for the presentation.
Thank you.
Any question from the audience? We are
I would
Just
like
a
to.
question, Andrea.
Yeah, just a quick one. So thank you, Anastasios, for this interesting presentation. I would like to ask you if the threshold that you set to understand whether a tag is blocked or not is fixed, or you have to change it if the scenario changes, or well, if there are some criteria to determine the threshold. Yeah, thank you.
Here you can see that the threshold for the phase disturbance was chosen to be 1 rad.
Okay.
The gamma with index phi Greek. This threshold was fixed during the experiments. Actually, we have tested more than one values in order to see which one produces the best accuracy. And we found out that 1 rad was quite satisfactory choice. However, to be honest, I'd like to make some differences in this algorithm and also include some diffraction theory in order to identify this threshold dynamically depending on the scenario. So this work has a fixed threshold, but in the future, I hope to change it.
Yeah, okay. So thank you.
Okay, so thank you for the presentation. Let's go to the next one. So the next presentation will be a flexible 3D printed UHF RFID tag for worker safety application by Chietera, Colella, Pirozzi Di Donato, Tomassini, Ferraro, and Catarinocci. I don't know if the speaker will be live.
Just a second, I need to share. Can you please just show if it's working? Oh.
Okay. Good morning, good afternoon, everyone. So today I'm Francesco Polo Chietera. I'm a PhD fellow at the University of Salento in Lecce, Italy. Today I'm presenting this work titled The Flexible Computing for Workers. And I'd like to highlight that this work has been carried out in collaboration with our colleagues from the Department of Technology and Innovation Science, Products and Supplements from the Italian Institute of Insurance Against Industrial Injuries, situated in Rome. This work This work has been done in the framework of the SMART project, which is financed by NOL, and it sees the collaboration of different Italian universities to realize a smart system for preventing or reducing injuries in agricultural working environment where remote control for machineries are used. Briefly, this is the system architecture that we developed for this project. It's based on the organization of a system mounted on controlled machinery that is able to locate and track the presence of obstacles. So if the machine goes too close to human work or an obstacle or too far from the control, an alert is produced. And this system is based on the localized localization system developed by our colleagues from this university, and has a very good accuracy under the meter, but its reliability is based on the presence of a redundant number of UHF-RFID tags to tag obstacles. And speaking about obstacles, one obstacles are the most challenging ones, because the human body can interfere with the correct working of common innate acts. So part of the project was select better configuration of tags for human workers. We tried to different configuration on different PPEs and security vests, and even if preliminary results got better results for the helmet, we decided to go further investigating the configuration on the vest, the security vest, because of some constraint about the distance between each tag that has to be higher than that of the helmet. And the problem with the vest is that if you put the tags directly on the vest, they are very close to the human tag. So performance degrades fast. So the first possible solution would be to enlarge the distance between tag and the body. We tested with a simple substrate of 5 millimeter, 10 millimeter, made by polypropylene, which has very low dielectric constant, so do not interfere with the antenna of the tag, and we can see that the maximum reading distance of the tag is like dramatically increase from 2 meters to barely 7 meters with the 10 millimeter substrate. But the problem is that this kind of substrate is rigid and is not applicable for comfortable work. Okay, so we need to develop to realize a design of flexible and power maintaining the realizing an antenna, pipa-like antenna with a flexible substrate. And this is the final design that we developed. The background is useful even to prevent some. And the top part of the replica has a meander structure that was helpful to fine-tune the frequency, working frequency. These are the final parameter size to obtain a good matching at 86 megahertz, which is the center frequency of the TSI band, which is reflected that. And then we try to realize a prototype, a flexible prototype, by using two technology. First, using 3D printing to realize the substrate, the flexible substrate, using a commercial TPU filament by Grips and the commercial low-cost 3D printers and Pujani Plus. And those tables are the parameters that we use to print the substrate. They are provided by the manufacturer. So then the most important one is the infill percentage. The infill is the amount of material that is used inside the structure, the 3D structure. It's very low for two reasons. One is that this way we can increment the flexibility of the final substrate, as you can see by the picture. The other one is that we would like to have a low dielectric constant. So the more air is inside the substrate, the lower dielectric constant. We measured it using well-known method of the theory resonator, and we find a value of 1.56, which is quite good for our scopes. Then the conductive part has been realized using high conductive nylon-based textile fabric from adafruit that we shaped using a cotton proper to obtain the final shape. And I would like to highlight that near the feeding point, we used two little sheet of copper tape to reinforce that point in order to enable the soldering process on the feeding point. Otherwise, it would not be possible because that damaged the textile. And we measured these antennas. We soldered an SMA connector to the point, and we measured the complex impedance of the antennas, DNA. And as you can see, the black line represents the real and imaginary part of the measurements, while the red lines represent the simulations, and they are very important. To further measure these antennas, we desoldered. We substitute the SMA connector with the commercial terminal chip for UHF FAD communication. We used an MG Monza 6, and we measured the performance, the two most useful performance characteristics of the tag, which are touch sensitivity and maximum and estimated maximum reading distance, using a lab-made characterization system developed by some of the authors. And you can see the results. We have the solid black line, which indicates the touch sensitivity that is very times 70 dBm. That corresponds to 6.8 meter of estimated maximum distance, which is quite good. And to further test and confirm this value, we realized that testing working conditions. We put our flexible tag in a bag on top of the security chest, and we'll be worked by one of our inspections. And we test the maximum reading distance using a commercial angle reader Arctic HH3, and we found that the maximum reading distance is 6.6, which is what characterization system. So we confirm the goodness of the provision method of the realized. Concluding, we designed for a flexible wearable UHF perfect tag in the framework of worker safety application, and realized a fully workable prototype using two different techniques: fused filament fabrication and the use of a good block to shape conductive flexible plastic. And the prototype performance would be that for the performance types of complex sensitivity and compare them with the results, and the results are very good, everyone. So this proves the goodness of the prototype. So thank you very much for your attention. If you have some questions, I will try to answer.
Thank you, Francesco. Any question from the audience? We cannot see. We cannot hear too.
You can use different 3D printing technologies. I mean, for example, in this case, we use 3D printing just to realize the box. Okay. The conductive part can be challenging to realize. Even if you can do it using some industrial machines like aerosol jet printing to jet print silver-based material. So it strongly depends on the technology that you use and for which part of the tag you like it. I think that 3D printing could be competitive in many applications, but if you need some customization of the final product, it's not competitive in an industrial larger number of devices need that case additional manufacturing process cannot be held.
So thank you.
It's my main research topic, so I agree with you.
You have to enable me to share my screen. I am the third speaker, but I am not able to share my screen. I don't know why.
You should be able to share your screen because I added you as co-host.
Can you see my screen now?
Yes, it's loading. Okay, yeah.
Okay. So thank you very much. So the next presentation is related to a UHF RFID smart system for worker safety, a hierarchical approach for localization, read by Bandini, Motroni, myself, Marracci, Patellini, Di Donato, Pirozzi, Tomassini, and Ferraro. So this is the outline of my presentation. I will describe the framework of the Synergy project and the application in this context of a synthetic aperture radar localization method for worker localization. In particular, I will describe a novel hierarchical approach to reduce the computational times and so to face the real-time requirement of the system, and then I will show the numerical analysis result and I will draw some conclusions. So the Synergy project aims to develop a smart energization of machinery assemblies with wearable radio frequency identification devices. The project was co-founded by the Italian Institute Against Accidents at Work, and the main objective is the development of a smart system to help to support the worker during the maintenance activities by ensuring that each operation can be performed in a safe way. So the so-called LOTO, lockout tagout procedure, became smart thanks to the if all workers present in the surrounding of the machinery assemblies are in safe position throughout a localization system. We evaluated the possibility to employ several technology at the starting step of the project, so Wi-Fi, Bluetooth, or Bluetooth Low Energy, ultra wideband, and so on. But we decided to adopt the passive UHF RFID technology since it offers the possibility to install passive devices with low cost, low maintenance activity on the personal protective equipment. Then, to perform the localization, we decide to adopt a synthetic aperture radar method which allows for high accuracy throughout a moving UHF RFID reader antenna. So we have to think about the step procedure. So if all workers are in safe position, the further step is allowed. Otherwise, the step is forbidden and the machinery energization is prevented. And it is very crucial to avoid any accident at work. How to implement the reader antenna motion? We decide to adopt a 3D Cartesian robot above the machinery assembly, able to guarantee a three-dimensional trajectory of the reader antenna. This allows to perform the tag localization with very high accuracy for the three coordinates. Moreover, to increase the reliability of the system, multiple tags are on the worker. So we can have tagged shoes, tagged Gillette, tagged gloves, and so on. So all the information about multiple tag can be jointly used to increase also the tag localization. So we measured the phase of all tags on the worker. We derive from the sequence of phase the phase difference, since we want to release from any calibration procedures of the offset term, and then we adopt a phasor notation to phase the 2π phase amplitude. So we assemble a vector of phasor from the phase sample. Then, since we know the trajectory of the reader antenna performed throughout the 3D Cartesian robot, we can assemble a similar vector of phasor that can be matched with the measured one. This matching operator allows us to build this kind of cost function, which minimum argument allows for the estimation of the tag position. So we have to solve a minimization problem of the cost function, and we decide to adopt a hierarchical approach to reduce the computational time. So in a first instance, we can try to perform an exhaustive search of the minimum in a dense grid of points to get the high resolution in the tag position estimation. But to avoid this, we perform at first an exhaustive search on a coarse grid of points to find a first minimum solution, and then we refine the solution by adopting an interior point method, a very fast interior point method, to converge to the global minimum. Okay, so we perform the algorithm solution in 2 different steps. This procedure can be seen as an alternative of a particle Zuor optimization, whose particles are initialized in the same point of the coarse grid of points. And this is for us a benchmark in the evaluation of the method performance. So we will show some numerical analysis to demonstrate the functionality of the proposed algorithm. So we consider a 3-dimensional trajectory composed by three main linear portions, and we suppose to know it with negligible uncertainty. Then we, to evaluate the localization uncertainty, we propagate the uncertainty on the measured phase sample throughout Monte Carlo methods. In particular, according to the commercial reader datasheet, we use a uniformly distributed error for the phase sample in the interval between -0.1 to 0.1 radians, and we consider 100 random tag position in the area, and we repeat the experiment 100 times for each tag position. So this is a representation, a counterplot representation of the cost function with respect to the x and y coordinate. Without loss of generality, we will show you the 2-dimensional localization performance. So in this case, the interior point method rightly converge to the global maximum. And in this case, we're starting for a grid of points with a step of 20 centimeters. I mean, 651 points in the domain. What happens if we try to reduce this grid step? It occurs some problem. In particular, if you use a very large grid step, I mean 2 meters, it could happen that the interior point method fails in converging to a local minimum. So we need to avoid this situation. So this means that we need to properly choose the grid step. To decide the right value, we try to evaluate the failure probability. So the failure probability corresponds to the probability to the algorithm convergence to the local minimum rather than to the global one. So the we investigated bivariate distribution of the estimated tag position for a grid step of 20 centimeter with guarantee in all the considered phases the right convergence to the global minimum, and this distribution has been adopted as benchmark. From that, we evaluated the standard deviation of the marginal distribution, and in particular the circumference with the radius derived from the standard deviation for a correct tag estimation. So we found that only when the a particles war optimization succeed to determine the right tag position, even with a coarse grid step with 1 meter step, the interior point method, so our hierarchical approach, need to start from 20 centimeters. However, so this can be as the right choice for the application of the method, and in any case, the main advantage of our approach is evident by considering the computational time. So with respect to a particles war optimization, we are able to notably reduce the computational time. So to conclude, in this paper, we propose a novel hierarchical approach to reduce the computational cost of RFID cell-based method for real-time localization of workers. That is a key feature when implement safety system. So if we properly define the method parameter, we are able to correctly estimate the tag position within the limit of the measurement uncertainty. And actually, the 3D Cartesian robot is under development. I'm sorry, but it is not properly working yet. So I hope that we can be able to show the real functionality in next conference. So I'm open for questions, just quick since we are a little bit late. Otherwise, you can write me later. Any questions from the audience or from the chat? Okay, so I'm going to go to the next speaker. The next paper is a transmission and receiving power profiles for RFID tags performances evaluation by El Haji Shahed, Uguen, and Kolarden. In the meantime, I will ask if the last speaker is online.
Yes, it's online. Yeah.
Okay.
Where is your presentation?
I will check if the speaker of the last paper is already online or not.
The last one?
Okay, I can see him now. Okay. So thank you. So please go.
Just a second, we need to set it up from the USB stick.
Okay.
It's okay. Which one?
Yes. Who is the speaker? Ali, Bernard, or you have to run the video?
Just a second, I need to set up the presentation.
Okay, but is it the speaker online to answer?
No, he's live. He will be presenting live. He's here.
Okay, sorry. I cannot. Okay, I can see him. Okay, thank you.
It's okay. Just a second, just so I can. You can try it. Okay.
Hello, everyone. Thank you for the opportunity for my presentation. My name is Adi, second year PhD student. And today I'm going to present my paper entitled Transmission of Specific Power Profiles for RFID tags performances evaluation. So the outline of this presentation is the following. First, I will give an introduction about the sport. Then I will go over the experimental aspects. Then I will go over the tags performance analysis, and I will conclude. So the introduction of this paper is the following. First, to present an experimental technique for characterization performances of RFID tags, and to present the power profile on transmitting and receiving based method to access the IC effective sensitivity, noted as the IC effective, and another quantity derived from it, it's the tag quality factor, QDB. And to compare several RFID tags using the proposed technique. And finally, to present the evolution of these quantities with respect of the transmitted power. Showing the RFID characterization platform used for the experimentation. It has 4 antennas connected to the Alien 9900 plus. One antenna is fixed on the main right of 5 meters, and 3 antennas can go on gantry on the left, one on the right, and one on the top of the gantry. But this presentation only explores the fixed antenna. The tag support, as we can see in the middle, can be translated and rotated, but we only explore the translation of the tag. Now going over the experimental setup, it's based on a joint variation of distance and transmitted power. So the tag support has been moved from 0.25 to 4.83 meter with a step of 48 millimeter. At each position, the transmitted power has been swept from 15.7 to 30.6 dBm with a step of 0.1 dB. This capability of the Alien 9900 Plus to sweep its transmitting power was the main key to obtain the activation profile. Here we can see an photographic for the main right connected to the antenna and surrounded by observing panels. That's the result obtained from the experimentation. We have obtained 2 distance profiles. The activation profile, which is the minimum transmitted power required to observe a tag response, presented in blue, and the second profile is the received power profile obtained at maximum transmitted power, represented in red. The maximum transmitted power is 30.6 dBm. We can observe a discontinuity in the middle of the figure because of the high fading, high loss in the environment. The activation profile is an increasing function of distance, and the received power is a decreasing power of distance. Now going over the construction of a proposed RFID tag figure of merit. We have introduced the IC effective sensitivity formula. It has been called the IC effective sensitivity because it's an approach for the theoretical sensitivity of the chip that we can find in the data sheet. And we can see the formula depends from the 2 profiles defined before, the transmitted the activation power profile and the received power profile. The offset between the typical sensitivity and the average over distance effective sensitivity is an important information and has been called the quality factor, QDB. Those quantities have been constructed for different tags, as we will see later. Now adding and bringing the effective sensitivity obtained from the activation profile and the received power profile, it has a horizontal variation and it's near, like almost equal to the theoretical sensitivity of the Monza 4 used tag of minus 17.4. It was obtained from the data sheet of the IC chip. Since the variation is technique, we have compared the power profile of different tags that has been experimented in the same conditions. In the first line, we can see tags of Monza 4 chip, but different antennas. Second line is a 5 tag with different antennas. and third line different chip and different antennas. And we define some criteria for evaluating the performance of the tag. The minimum distance at which the tag does not respond. The Dmax is the maximum distance at which the tag has responded, and the QDB, as we defined before, is offset in dB between the typical IC sensitivity and the effective IC sensitivity. And rho RR is the read range ratio. As we can see, all these commercial tags has a good reading range ratio and the QDB value equal to 0. That means that theoretical sensitivity is almost equal to the effective sensitivity profile. Only for the last was designed to work on the dielectric surface, and that's why it had a high value of Q and a low value of rho RR. We have calculated the PIC effective sensitivity, the mean of the PIC effective sensitivity at each transmitted power. And this variation in blue that we have observed is linear. Also, the QDB values was derived from the PIC effective sensitivity, and its translation from it, and it's represented in red. As we can see, we have a quasi-linear variation with a slightly different slope from one tag to another. And this quasi-linearity can be explained by the nonlinear behavior of the tag with the applied power. To conclude, we have proposed an original technique for combining transmit and receive power profiles in order to access an entrance characteristics called the PIC effective. Also, we have proposed a new tag, figure of merit, QDB, and we have observed a linear variation of the effective sensitivity over the applied transmit power from our experiments, as we have seen. And this technique can be advantageously used to compare performances for UHF RFID tags. Thank you for your attention. I'm ready for your questions.
Thank you for the presentation. Any question?
Yeah, I have just one.
Okay.
Which is the power presentation of the video? Because you have to evaluate your distance by varying power.
Yeah.
Well understand. So, how much is the power of this presentation? 1 dB, 1, because I think your graphs are quite continuous.
Yeah, the resolution you mean. It's 0.1 dB. That's what we used as the resolution here. The minimum resolution is 0.1.
Something like 9,000
9,900 plus, yeah. It has 0.1. Yeah.
And dips. Yeah. How does it change? Or
okay, I will make sure that I understand the question. You asked me if I measured the MOSA 6 and the NXP.
yeah, or some other altitude, so the chips change their.
Yeah, that's what we saw. We have small variation, and as we have seen that by changing the transmit power, the sensitivity has changed as well by a linear variation. And also, it was measured. I think the NXP you called 7, and the MOSA 6 as well. MOSA 6R has a good, really good design and really good reading range. Yeah. Not over the distance, but not over the transmitted power applied. For we have the receiving power in red. The green plot has been obtained from the red one, but this red one, it was at maximum transmit power. But we have changed the transmitted power to observe. We have obtained a lot of red plots with different transmit power, but at each received profile, we have obtained a different mean of this green plot. And it was linear for all the tags, and that was strange at the beginning. But after that, we thought that it's a nonlinear variation for a chip, so that can explain this.
Meter ID technologies positioning, locating applications with sub-centimeter accuracy by Lynch, Adeyeye, Hester, and Tenzeris.
Okay, I will play the video.
Okay, so
Second, please.
Adeyeye, sorry for my pronunciation online. So he can answer to all the curiosity later.
My name is Charles Lynch, and I'm a current PhD student at Georgia Tech. And today I'll be giving the talk titled MMID Technologies for Positioning and Locating Applications with Sub-Centimeter Accuracy. Now, for a brief outline of the rest of the talk. I plan on building the motivation for why you would choose 60 gigahertz localization, 60 gigahertz bands for localization. Then, I'll dive into the details of a cost-effective, compact system architecture for MMID localization system. The details of the MMID tag with their subcomponents will be presented, as well as a theoretical reading range estimation of the current and ideal future reader systems. Afterwards, the ranging and angle of arrival detection signal processing framework will be presented with their respective results, and I'll round out the presentation by drawing on the conclusions of the current work, as well as future systems and applications that this work can be expanded to. Asking the question, why 60 gigahertz for localization? Well, typical RFID, commercial RFID tags operate in the ultra-high frequency, or UHF bands, which are inherently limited due to the limited in ranging resolution and accuracy due to the limited bandwidth resource, which is restricted by the FCC. By shifting to higher frequencies, one can gain the added benefit of the bandwidth resource by a factor of roughly 150 times that of UHF band, in particular in the 60 gigahertz band, as this band, which was recently updated by the FCC to allow 7 gigahertz of continuous bandwidth. In addition to this valuable bandwidth resource in terms of localization, this also enables highly compact and affordable system components. Google, for instance, shown here with their Soli chip, has even integrated this FMCW radar system into their Pixel 4 product. Therefore, the affordability and compactness of these system components enables inconspicuous sensing applications, and as well as for localization and tracking systems in future technology. Diving into the proposed MMID or millimeter wave identification localization system. The system is composed of two components. The proof of concept reader, which was selected, was the IWR 6843 AOP module, which is a MIMO-enabled, low-cost form factor antenna on package, frequency modulated continuous wave radar module from Texas Instruments. This module has 3 transmitting and 4 receiving elements, which constitutes a field of view of plus or minus 90 degrees centered at bore sight on the radar. The other component is the MMID tag, which is a semi-passive, low-cost, and sticker-like form factor that enables surface-agnostic operation and a total footprint size of 3.5 by 1.5 centimeters. But the size of this tag can be reduced to roughly 1 by 1 centimeter with further optimal placement of the system, of the circuit components of the tag itself. Into the details of the MMID tag design. There are 2 main subcomponents of the MMID tag, namely the RF front end and the baseband circuitry. Both play a critical role in the backscattering the MMID tag response back to the FMCW radar, and as well as the power consumption of the MMID tag itself. The RF front-end design is made up of two components, the antenna and the modulating load. These components play a critical role in the reading range of the localization system. The performance of the S11 or return loss is displayed on the graph in the middle with a minus 10 dB matching over the operational bandwidth of the radar from 60 gigahertz to 64 gigahertz, as well as a peak gain of roughly 4 dBi. Because the backscattering nature of the link, the antenna therefore would count twice in the reception and reflection of the interrogation FMCW radar signal, and therefore provides adequate performance for close range operation. The other component is a modulating load, as previously mentioned, with the two modulated load states plotted in the curve on the right, providing sufficient enough modulation depth in between two of the states, enabling the detection and further localization of the MMID tag. Band circuitry is used to drive the modulating load of the front end, and is comprised of a low power voltage regulator, a resistance-based voltage-controlled oscillator, or VCO, and a voltage divider. The regulator maintains a stable supply voltage to the VCO for stable frequency generation, and is important due to the frequency of the MMID tag acting as both the ID as well as encoding the localization information on the return signal. The voltage divider is necessary in order to set the appropriate bias voltage to the modulating load. And then below in the table, you can see the power consumption breakdown of both the RF front end, the baseband, and the fully integrated MMID tag. This can be further reduced by selecting a diode with a lower turn-on voltage, as well as depends on the frequency of operation or how fast you're switching on the VCO circuit as well. But provides a suitable low-power proof-of-concept MMID for localization. Having designed and characterized the presented MMID, a simple link budget analysis is presented for the current reader system and a future ideal system. While the current reader has only a maximum reading range of 90 centimeters, this is due to the low gain of the tag and the system being copolarized. By increasing the tag detectability with a retrodirective structure or a high gain structure, and switching to a cross-polarized interrogation, the theoretical maximum reading range can be envisioned to over 48 meters, and therefore enabling long and medium high-fidelity localization and tracking applications. Diving into the ranging signal processing framework. Due to the nature of the FMCW radar interrogation, a scatterer that is in the field of view of the radar will be linearly proportional to the baseband intermediate frequency based on the time of flight of the two-way propagation of the return signal. However, because the target is modulating in frequency, the MMID response will be displayed at the corresponding baseband frequency, as shown on the plot on the right, at roughly 23 meters in the frequency domain. But this is mapped only to the actual ID of the tag itself. And encoded in this, by taking a difference of these two plus and minus frequencies, one can obtain the range of the MMID tag from the radar itself. Now, due to the static clutter, due to the tag being static for the ranging measurements, one can take a set of 108 chirps, which is in a single frame of the radar, and spectrally average the ranging FFT shown on the left together to form an average range FFT shown on the right. One can see on the right that there is a great deal of clutter at close ranges to the radar. This is due to the phase noise as well as all the static clutter in the environment from interrogation. Another added benefit of the modulation away from this static clutter is you're very easily able to detect the tag at the ID frequency in the baseband without the need of any further signal processing that needs to be done for real-time localization of the tag itself. So now using this ranging estimation, the MMID was steps from 15 centimeters to 50 centimeters in steps of 5 centimeters, with 100 range observations recorded at each step. The average ranging error was bounded to 0.5 centimeters over the ranges recorded, thus enabling close range, sub-centimeter accurate localization for future cyber-physical systems and tracking systems. Additionally to the ranging evaluation, the angle of arrival signal processing framework utilized a similar method. By utilizing the difference between phase of 2 receive channels on the low-cost FMCW radar, the angle of arrival information can be obtained. This is done through taking the phase of the range bin at the MMID tag located in the range FFT, and then taking an angle FFT across these 2 phase values. 128, the same 128 angle FFTs were then obtained and then averaged to obtain an average angle of arrival estimation of the MMID tag itself, as shown here down below. The MMID was evaluated in terms of angle of arrival at a range of 15 centimeters from the FMCW radar and positioned from minus 40 degrees to plus 40 degrees in steps of 20 degrees, with 100 observations of the AOA estimate being recorded. The results from the measurement can be viewed in the table on the right and highlight an angular accuracy within 1.79 degrees of the true angle of arrival of the MMID tag, highlighting the 2D microlocalization capabilities of the proposed MMID system for close-range applications. Conclusion, the proposed MMID localization system enables sub-centimeter accurate localization while providing highly compact and affordable system, as the whole system with the tags included retails for roughly $20 at scale. The system is limited in reading range capabilities, but with a retrodirective MMID tag topology, a theoretical reading range in excess of 48 meters can be envisioned for long to medium to long range fine-scale tracking of robotics and automation systems, thus highlighting a potential paradigm shift in tracking technologies, utilizing the 60 gigahertz frequency bands. Here are my references. And with that, thank you for your attention.
Thank you so much. Any question from the audience or from the live participant? We can conclude this technical session, this special session, with just 3 minutes late. So thank you to the workshop organizer and to all the authors which contribute to this technical session, and I hope you enjoy the session and see you next year with this and later with the next papers. Thank you again.
Amrung.
Znači on biti virtualno.
Virtualno svijeta, možemo uključiti se, ja.
A ja ne mogu. Može idem sam sebi.
A da možeš mi poslati for. Amrung ime, a prezime ide dalje, kao se i sam. Može li uključiti mikrofon pa da ga pitam? Ajde. Ano. Thailand. And on the University of Spain. Vama što znači ako vi znate unaprijed da ga trebate pustiti sa noga, tako.
Ono kao video ili...
Jer on to...
Samo mora reći kao hoće video ili će sam...
Yeah, because we're gonna be delayed for 10 minutes because the keynote speech was late, so there are some people there. So the conference chair asked if we could delay for 10 minutes. So.
Thank you. Da ne mogu.
Amrung ne reagira. Reagira. Računao da nije jasno reagira, ali dobro. Bit će ima. Ali on ima dva svoja papera nazad. Amrung.
A ovo su ga neki kao po nečem njegovom. Kao u radu, nećemo predati.
Vidite kako je ovdje. To je ovdje nešto krivo tiskano. I ovdje u programu isto su dva rada. Samo što na jednom je naveden kao University of Riga, na drugom je taj. I ovdje mi isto tako piše. Amrung, dva rada.
Ovo je moj četvrti rad, sinoć ga ja pozivila, pa ja ga dodan, a kad se ovo tiskalo još nije sjetio to. A ovaj njegov prije rad, on nema video link za njega. A ne, ovo je od... Jedan. Ovo su oni ova Register su... Ok, ovdje nema videa uopće njegov.
Nije upload. To znači da mora prezentirati uživo.
Ali će to nešto.
Tri, četiri, pet, šest. Ono kako bi ovo izgledalo. Ono možda reći, ali ovo, da li si se sakut, mislim, da li si je sakut.
Ono od jutra je bilo. Ovo nije sebi dozvolio na laptopu da uopće može koristiti. Ono jutro skrebi.
Da, znači da njega...
Mi ne možemo, samo može on.
A ono, poslije kad se spoje, ja spojem preko mobitel.
Aha.
To je onda radio. Trebam javiti ovom ustvari, da on čuje da je odpođe na 10 minuta.
I on čuje sve.
Jesam čuo sam, sve u redu.
Super. Poruku da imali prezentaciju za ovaj. We have one presentation uploaded.
You're the first.
Been recorded, or are you going to present live?
A svi su dodani, sinoć do 2,5. A nije njima stoji normalno, to tako je.
Dobro, ovdje stoji kasaca.
Htjela pitati jer vidim prezentaciju. Da li vidite vi prezentaciju vašu?
Vidim.
Dobro.
Tripalo malo tamo, da ne bude
Vamos se spoja i grazie.
You want me now?
Mr. Bamrung, do you hear me?
Yes.
Yes. So, do you intend to present your live or?
It's up to the session chair, but there was the email from SpliTech was in my spam folder, and they said that my video has a problem about the voice. Okay, there is no audio at all in the video clip. For the paper number 3 passive pursuit, they upload the video for paper number 4 soft homotopy. I think that video is usable.
Yes, it is. But we don't have a basis.
Do you want me to present it online right now, or?
No. When your turn comes, we have three.
Okay.
Okay. Now you can turn off your microphone.
Okay, I turn it off.
Thank you. Okay. Good afternoon, everybody. Welcome to this third and final session of the engineering modeling track on SpliTech2022. My name is Vitko Doric. I'm from the University of Split. I'm going to be chairing this session. So we have 6 papers planned for this session, and I think the best thing is to start right away with the first paper. It's entitled In Plane Displacements of Thin-Walled Curved Beams. It will be presented by Dražen Kustura from University of Split. Actually, he's not here, so we're gonna watch a pre-recorded presentation, and then he will be online available for any other question. So please start the presentation.
Hi, I am Dražen Kustura. And I present a paper titled In Plane Displacements of Thin-Walled Curved Beams. After a brief introduction to the problem and expressions for this analysis, the solution we presented includes 4 compared with solutions of other researchers and the results of the shallow finite element model. Middle surface of thin-walled curved beam with a double symmetric I-shaped cross-section is shown in the figure on the left as the coordinate systems used in this analysis. Where a curved beam with H cross-section on the right. Point P is an arbitrary point on the middle surface. A small number, the approach is used to obtain the coordinate expression for thin-walled curved beams. In this paper, a simplification of the approach presented by Young incorporating the longitudinal displacement of the arbitrary point is presented and in comparison approach. The in-plane force is now also considered. The static analysis of thin-walled curved beams complex due to the coupling effect of internal forces. When the cross-section is symmetric, Then in-plane out-of-plane analysis is uncoupled. In this paper, involved waves floated in plane and Croatia are analyzed, presented close form solutions. Assuming that the material is linearly normal stresses, normal strain variation is as follows. If there is no distortion of the cross-section, then the transverse displacements at point B are as follows. And if the deformation is small, then these strain displacements relations can be used. If the shear strain of certain surface is invariant, that is, if the middle surface shear strain is zero, then this is the expression for the longitudinal displacement of the double symmetric cross-section, and this is the tutorial for the meat. These are the expressions for the double symmetric cross-section. The last term is different from the large cross-section because of the curvature. In this paper, involved curved beams, double symmetric cross-sections are analyzed, where general law is applied in plane and curvature. Consequently, the in-plane, out-of-plane displacement and internal forces are uncoupled, while the out-of-plane displacement and the out-of-plane internal forces are zero. In this case, the expressions for longitudinal displacement in flow and external stress are the same for both types of cross-sections. If the curvature is approximately as follows, then the resulting expressions are simplified and approximated. Furthermore, in this case, the cross-sectional properties of the curved beams are the same as for straight beams. The cross-sectional results of normal stress required in this analysis are defined as follows. While the plane force follows from the equilibrium. Since for the double symmetric involved curved beams, all internal forces and distributed line loads are defined with respect to the curved line and infinitesimal segment straight line in plane internal forces is shown in figure 2. In this case, the higher order terms results in these equilibrium equations. If the distributed line loads are invariant, if the axial and shear force are eliminated from the equilibrium equations, then these equations are obtained. And as a result of this governing equation, there are solutions of this governing equation, these unknown coefficients, which are determined with the method initial parameters. Is the governing expression for the method initial parameters, where the state vector and initial state vector are defined as follows. The expression for the boundary conditions can be found in table 1, and this is the expression for the field matrix. The boundary conditions, geometry, thin walled, quarter circle, cantilever beam, double symmetric, H-shaped cross-section, loaded at the end, free end, radial force are shown in figure 3. While shell finite element model based on this being shown in figure 4. The The results of this finite element model are practically the same as those of the model presented by Kimet. Basis and in principle at every end of the frame are shown in table 2, while the way for the normal stress beam at the beam are given in table 3. The results presented in this paper are in excellent agreement with the original finite element. The discrepancies compared to the finite element model is smaller than the discrepancy of the finite element model based on theories of relatively energy machine. Also, the absolute values of the normal stresses at the flange junction are the same for FAD and FAD. Well, the way presented in this paper and finite element model paper. In this paper, a simplified calculation of the longitudinal expression and in plane static analysis involved curve beams double symmetric A and H shaped cross sections was presented. The analytical solution obtained using the initial parameter where the curvature approximates. The governing equations of this approach are obtained using the free-body approach in which the discrete line loads are neglected, while shear force is considered. That is, the shear force is correlated with the normal stress cross-section resultants. A good agreement on this analytical solution which our finite element model was true. And finally, thank you for your attention.
Okay. Thank you. So the paper is open for discussion. Are there any questions? So if there are no questions, thank you, Mr. Kustura, once more, and we could move on to the second paper entitled Modeling of Crack Propagation in Welded Structure Using a Separated Phase Field Approach. And the paper will be presented by Boris Jalušić from University of Zagreb, Croatia.
Samo tren da šeiranje.
Thank you, Mr. Chairman, for your introduction. The paper is actually dealing with the problems of computational mechanics, and we're trying to develop some efficient algorithms to model welding, and also in that we're trying to model the crack propagation efficiently. I have to mention here that the research is done through the project which is funded by the operational program Competitiveness and Cohesion, with my coworkers from the Faculty of Mechanical Engineering and the Polymath College from University of North. So this is the brief outline of the presentation. I'll talk something about introduction and motivation, why welding, recent advances in technologies in welding, how we actually can simulate efficiently and fast the process of welding. Then I'll switch the talk a little bit to the modeling of fracture using this phase field algorithm that we developed. I'll show one numerical example from the literature and show how the residual stresses and the plastic strains influence the crack propagation and material softening and draw some conclusions. For the motivation, welding is, as you know, one of the cheapest and most widespread production processes of joining two metals. There is a lot of benefits to welding, but there are a lot of byproducts. This is actually due to the residual stresses and plastic stress that occur in the welded zone. In our civil engineering and engineering, there's always the balance of cost of welding with the mechanical properties of welding. So here I put on this in tables. You can see that single pass welding can actually come up to 30% cheaper than multi-pass welding for the approximately same technology, while the tensile strength and yield strength remain the same. There's a little bit difference in elongation and impact strength of weld material. So what we're trying to simulate here is welding in one go of thicker plates. Okay. So in order to do that, there is some kind of new technology proposed in 2017. It's called the buried arc method. It's actually a technology where the electric arc and the tip of electrode are buried under the surface level of the molten material. Higher welding currents and voltages are used in order to penetrate through the plate, and there is no need for this kind of hoops in preparation of this welding model. So Brač and co-workers wrote a nice paper in 2019 where they modeled butt welded thick plates. They did it also experimentally and numerically. In experimental measurements, they did measure the temperature profiles using the thermocouples, and with the hole drilling method, they measured residual stresses on some places, and after that, they compared that to their material models using elastic isoelastic material, and this quantum heat flux method, which is actually a method in Abacus when you're modeling the heat input using the deflux method. Okay. So we are trying now to improve that and replicate it. I have shown a few formulas. First, the welding is, as you know, highly non-stationary and non-linear process. So the most numerical simulations are done sequentially coupled. Firstly, the thermal analysis is solved where we calculate the temperature field, and then we switch it up to the mechanical analysis, where on the right-hand side we plug it in and solve the mechanical analysis for our displacements, residual stresses, and the plastic stress. In this approach, we try to replicate the same example using half of a plate, using something which is called the Abacus welding interface, or as we titled it, this is prescribed weld temperature. We're using three classical elements in the thermal analysis, and in mechanical, we're using the same analysis, but with incompatible modes. Firstly, I just say that the drawback of this prescribed temperature method is that you have to have either experimental results or some other numerical results, because you have to apply some kind of torch temperature, which is constant value, in order to obtain this kind of agreement with the other results. Okay, so these are two positions to the thermocouples and the residual stresses where the holes are drilled. If you have that and you model it with prescribed weld temperature, you can have the reduction in CPU time of 50%. Okay? And if you do some additional manipulation with temperature histories, you can go up over 70% in reduction. So I put some kind of I put some animations just to show you. This is the first thermal analysis. The speed of the welding here is about 30 millimeters a second. If I remember correctly, this is using the prescribed weld temperature and using the per element method in Abacus. So this will weld the two plates together till the end, and then there goes the cooling effect. I'll skip a little bit that because cooling takes a bit time. So when we get the temperature fields, we switch it up to mechanical analysis and then input it there, and we can obtain our residual stresses and plastic strength numerically. This is a little bit technical. So this is what is not the final picture, but it doesn't matter. So this is what we obtain. Now we can model welding efficiently, and after that we try to model actually crack propagation on the welded structure. However, since our experimental pitch equipment has arrived maybe a month ago, we still don't have our experimental results. So everything here that I'll show for this crack propagation is actually done on the example from the literature. A few words just on the modeling of crack propagation. There are two different approaches. There are discrete approaches and diffuse approaches. Discrete approaches tend to not work that good because the solution is highly dependent on the mesh, and you have to have numerically complex tracking of the crack discontinuities, while the phase modeling approach uses only a scalar damage variable here, which differentiates fractured and intact state. This variable can either go from 0 to 1, where 0 is intact and 1 is fractured state, and you have no explicit tracking of fractured surfaces. It goes so these are separate phase field approach. I have to put some formulas in. It's solved in a staggered manner, and it's solved in incremental iterative manner. What this means? It means that it has two stopping criteria in the iterative flow, which enable us to use larger increments and cut down further computational time, since phase field model requires smaller elements. So you have one convergence check here on this, for the displacement model. This is done for the abacus, and you have other here for the global norm of our scalar variable phi or phase field model. Okay? Displacement and the phase fields are determined in concurrent fashion, and everything is embedded in the software abacus using subroutines, UMAT, and UL. These are the governing equations, and these are the actual boundary equations that need to be solved. Okay. Just to explain a little bit of scene, master routine controls everything. You do the loading increment, you can put either force or displacement. It solves the displacement model and calculates this history variable, which is dependent on the length scale parameter, fracture toughness, and the positive part of deformation energy density. Passed into the phase field model, which calculates from this equation a variable of damage. Okay. Now we check the variable damage, or this is the L2 norm for the global model. If it's not below some kind of value you prescribed, we use here 0.5%. Then it goes to the displacement model, and this is done iteratively until this is obtained. Okay. Then at the end, it also checks for displacement and goes through the. Okay. This is our example from the literature. These are actually a plate 500 by 500, which they welded it longitudinally with a weld width of 26 millimeters, and they try to investigate the crack growth here in the weld zone B dash. Okay, but firstly they cut the empty specimen, but after that they also cut this is some kind of aluminum alloy. They also cut here the foam obtained specimen. These are actually the values in the picture that was provided for me by the authors themselves. It is 78 by 75 in order to further cut down the residual stresses. Okay. So they measured in the paper residual stresses of the CT specimen. These are these knots. And we, for the initial state, we just modeled the geometry and put in outputs using subroutines are one value. This is one value of longitudinal residual stress, which outputs converts to equilibrium of our foam missile stress. So this is the first start point for our verification model. there will be 3 models total, one without anything, without residual stress, one with residual stress, and one with residual stress and estimated plastic strains, which we here have to actually kind of guess and calculate through our nonlinear graph hardening model for the aluminum. Since we only have one component, we have to calculate the one-dimensional plasticity and incorporate this kind of total plastic strain inside the model. So then after that, we load it with displacement V in my direction to open it, and this is on the mesh of phase field model with 96,000 elements. And what do we get? I stored it here on the quarter value of the entire displacement. This is for the prescribed residual stresses and no stresses inside, and this is only for the prescribed pressures and plastic strains. As you can see, there is a difference, and the plastic strains tend to slow down the grain propagation inside our model. Okay. Just to show that on the animation, and please, okay. This is the continuous damage state of the city specimen without any prescribed stresses and with prescribed stresses, since you can see here that we obtain the same solutions. So residual stress has no effect on the crack propagation here, while if we have plastic strains, you can see that we receive about 20% more force if plastic strains inside. Here is the main problem for us now, because when the material begins to soften, the analysis seems to not converge anymore. We are looking into it and we know what's the problem, and we're going to solve it before we publish the paper. So let me just go through what I presented. We presented the numerical simulation of arc welding. Prescribed weld temperature was used since it is in good agreement with the experimental results and the other numerical simulation, and with the 50% less computational time. And after that, we did some trap propagation problem. We observed physically correct trap propagation for this CT specimen, and we can conclude that initial residual stresses have no influence on the crack propagation, while plastic strains slow down the crack propagation and influence the convergence of the numerical method. In further research, we'll try to model and use this kind of methodology in fatigue problems. Okay. Thank you for your attention, and if there is any question.
Do we have any questions? I have a question, but I'm not going to risk now because it's not my field of expertise, so I don't want to ask you something very stupid, so I will rather ask you. Thank you very much. And I think we could move to the next paper. It's entitled Implicit Explicit Error Indicator Based on Approximation, and it's going to be presented by Philip Stanisha from the other Stefan Institute.
Thank you. Thanks for the introduction. All right. So as it was implied, we are talking about this implicit explicit error indicator in our lab. So first, to give you an idea of how this presentation is going to structure, it's going to be actually quite short. I'm just going to go first through how we approximate our differential operators. This is going to be like just a brief overview. And I'm going to present this error indicator itself, just how it works, its basic logic. And then finally, I'll round it off with an example. So we are trying to approximate continuous functions in discrete spaces. So for this, we use radial basis functions, and from this we can also approximate differential operators of these continuous functions, which we can of course use in solving diverse differential equations. So the philosophy here is that we can approximate a differential operator by constructing a local sum of function values at different points and their assigned weights. So this is if we here imagine like a population of discrete points in space. We are approximating, say, a differential operator of the central point here with the values in these orange points. So this becomes well, we get the weights for this equation here from this system of equations. This is done only with radial basis functions. This proves not to always be not to always have a solution and to not always be as stable as we would like. So this is then further augmented by adding these sets of monomials here. This can be of different orders, and it's been shown that this order of these monomials actually then kind of defines the order of approximation of differential operators. So this is all done by our C++ library, which is free to use. You can find it online. Here's the link if you would like to look at it. But yeah, this is just a short intro to the method. So this implicit-explicit error indicator, which I'm going to refer to as Emacs for the purpose of this presentation, is actually constructed as follows. So first, we need to find our approximations for our differential operators, both implicit and explicit ones. And the ones that we use for the explicit solution need to be of higher order than the implicit ones. Then we have a problem that we are solving implicitly, find the implicit solution of this problem. Then put this solution into our explicit operator, which should be like representing the same equation as the implicit one. And this gives us actually back the right-hand side of the initial equation, and we can compare the two. And from this comparison, we should be able to indicate areas of high error. So if I show this in form of an example, this is going to be an example of Poisson equation, which is defined by this set of equations here, which I'm not going to go into too much details. But anyway, what's important is that this right here is the right-hand side, so this is going to be the thing that we are going to be comparing our later explicit solution to. Then we have also the definitions of Dirichlet and Neumann boundary conditions, and we have here a circular 2D domain where we are actually solving this equation, and it has mixed boundary conditions. On the left-hand side, we have Neumann boundary, and on the right-hand side is Dirichlet. And the Poisson equation itself has like, if we are looking at this, essentially analytical solution of it, it has a strong source here, and then it kind of fades. And this is shown in the actual solution of this. So you can see the strong source that I was mentioning over here, and then it fades towards zero for the rest of the domain. So this is the implicit solution that we obtained. And now we use this, put it back into the equation, solve it explicitly, and this produces, well, it should produce, well, this expression here. And this is what we are comparing it to. So Emacs, so the indicator in question, shows that there's, well, this is actually plotting absolute errors of both, so of the actual analytical solution versus implicitly obtained one, and Emacs as I described before. And we see that around the strong source we get most error activity actually. So to show this at a different angle, you can imagine y equals x line plotted across this graph. So like so, and we plot our results along this line, and you see that Emacs, the actual error and solution kind of coincide in this strong source. And here I'm also at the same time showing results for two different kind of Emacs. So both times the implicit differential operators are of second order, and the explicit ones are of fourth and sixth order respectively. And you don't see any major differences apart from maybe here there's like a small bump, but it doesn't really matter. The error indication seems to be working quite similarly. So the order does not, I mean, how much the order is higher does not really affect the results that much. So finally, I've presented this error indicator. It has some promising well, abilities to indicate errors, which is supposed to be its purpose. We've only used it on a simple problem right now, but it's shown that the order of the higher order approximation does not really matter that much. And we are looking to use it on maybe some more realistic problems because this was just a really sterile one. Finally, I'd like to thank people who support us financially, and also to all of my colleagues who are also here today. They're making my life easier every day. Make me want to come to work. So, and also thank you for being here for this presentation. Thank you, which is nice and emotional.
Yes, I can hear you. Okay. Let me find where is Google Meet. Oh. Yes, I'm finding the way to share the screen. How? Oh my God. Okay, yeah. This one. Yes, okay. Okay. Can you see my screen? Okay, you can see my screen, right? Okay. Okay, I'm sorry for that. Okay. This is the okay. I'm not sure the time now. Good afternoon, right, to you in Croatia, but it's 10:30 p.m. here in Thailand. Okay. The paper title here is Basis Pursuit and Linear Programming, as the session chair has introduced it. My name is Bambung Thao Siskun. I'm from Department of Electrical Engineering, Faculty of Engineering, and the university is the Srinakhri Middle University from Thailand. And the paper is intended to present at SpliTech at in Croatia. Okay, the contents in this paper will be the following. We will consider the basic thing, which is the introduction in comprehensive sensing, and we will have a short look at the Basis Pursuit, which is the main algorithm here. The paper would like to formulate in another form, and we will present the contribution from this work, which is the linear programming forms. Okay, it has two forms actually for the Basis Pursuit algorithm. The Basis Pursuit is the classical method, which is quite powerful in comprehensive sensing when we want to get back or recover the sparse signal or data. Okay, and we verify the equivalence of the linear programming in terms of the numerical computer simulation, and we will see a little bit the benefit of the linear programming form, and finally we will talk about the conclusion of this work. Okay. In science and in engineering, we need to recover the data, the input X, okay, and input X is transferred to, for example, in wireless communication, we have the wireless channel here, or in control system, you may have a transfer function, and at the receiver or at the observation side, you may have the perturbation or the additive noise due to the imperfection caused by the random noise or the thermal noise in electronic circuit and so on. And here is what actually we receive. Okay, this model can be expressed as the linear system, simple linear system like this. And in this work, we have short time, and we didn't include the effect of the perturbation or the noise at all. But in my other works, I have already added. Okay, and the effects are quite different. Okay, but it's not included in this work. Okay, the Basis Pursuit is derived from this one. Okay, because the ideal or the ideal scenario for comprehensive sensing is that we want to minimize the data which has some elements that are zero, and they use the pseudo-zero norm. Pseudo-zero norm is the way you count the number of non-zero elements in this vector, actually. But when we program it into computer, it turns out that this optimization framework is combinatorial, and it's non-deterministic polynomial time hard, or NP hard. Many people try to avoid that. And one way to approximate this one is to use the L1 norm. And the L1 norm is known by the first author as the Basit pursuit. Okay, that's the name of the algorithm, which we will try to express it in a different way. Okay, in this work, we present two forms of linear programming for the Basit pursuit. Basit pursuit is nearly the same as the L0 norm, and here we use instead L1 norm. Okay, and this is the one norm. So the L1 norm is only the summation of the absolute value of each element of this vector. Okay, we don't count, we don't judge whether that each element of x is 0 or not, but we make the summation and we make the minimization. And it is well known that this optimization is convex, so it's quite easy to implement in many by using many softwares. Okay, we don't use the convex optimization. We propose two new alternative optimization frameworks. The first one is LP1. It stands for linear programming. One is the number one, first linear programming algorithm. So we minimize the summation of variable t. T is new variable apart from x. And the constraint is the same, which is the linear system, whether it's noiseless or noisy. The noisy will be considered in the future because we are running out of time. Okay, and the constraint has some more details like this. T minus x is greater than 0 for each element, and t plus x is greater than also 0. Okay, and yeah, we minimize the whole thing by two parameters, x and t. Okay, x is the desired vector and t is the helping vector. That's the first linear programming method. For the second method, we introduced also two helping parameters. The first one is vector u. The second one is vector v. Okay, our x is constructed from the difference between u and v, and u and v are concatenated in a vector like this. Okay, and this vector is called vector phi. So the vector phi could be found from the minimization of the product of each element of u and v, and the constant will be very similar to the typical one, which is ax equal to b, because our x is intended to be the difference between u and v, so this one is u minus v. And another more constraint are the following. U should be greater than 0 and v should be greater than 0. Okay, you can see two alternative formulations of the Basit pursuit, but it's expressed in linear programming. We can use any linear programming software, okay, which was developed several years ago. Okay, so the candidates for the computer simulation Basit pursuit, okay, that one that is of interest for many researchers, and linear programming number 1, linear programming number 2, which are two algorithms that are proposed in this work. Okay, for performance aspect, there should be no difference, because I didn't expect any benefit that the linear programming number 1 and number 2 could provide lower root mean square error from the Basit pursuit, because Basit pursuit is already very powerful. Okay, and yes, we express the error in terms of root mean square relative error with respect to the number of non-zero elements. So we can say that if we go to the left, the vector is very, very sparse. It means there are many zeros inside vector x. If we go to the right, several elements of x are not 0. So there might be more errors when x are not 0. Okay, and let's talk about the different aspect. The elapsed time of computation, it's like CPU time, the time that the processor that uses for the computation for the same task in comprehensive sensing. The linear programming number 2 that involves U and V take quite long time. Okay, I have to wait quite long time, and linear programming number 1 and the basic person consume almost the same computational time. And let's talk about the RAM, or the memory that is occupied during the computation in computer. The linear programming number 2 occupies quite a lot memory in terms of megabytes here. And linear programming the basic person is the blue one. It's quite large at the beginning, and linear programming number 1, which is the red one here, consume or takes or occupied less memory than the basic person, and the other for the high non-zero elements, a high number of non-zero elements, both are quite nearly the same. Okay, conclusion of this work is that we propose two basic pursuit alternative in the form of linear programming. We found that the equivalent basic pursuit in terms of linear programming provide the same error as the basic pursuit original one. And one of the basic pursuit equivalent linear programming takes the same computation time as the basic pursuit, whereas another one lasts longer in the computation. The first basic pursuit linear programming of equivalence consume nearly the same amount of required memory as the basic pursuit, but another one, the second one, occupies significantly more memory in the computer during the computation. Because this I'm not expert in linear programming solver, maybe some other researcher maybe could find the more efficient software and we can implement this formulation, the linear programming one, and it can happen that the occupied memory and the computation time might be less than the one that is required by the basic pursuit. Okay, that's all for this presentation. Thank you very much. sensing of we see the basic idea in decision criteria. You see the conventional method, which is homotopy, entropy, we see the proposed idea, the first one, is based on conventional method. We use the working routine. Another one is the minimal version. Is reduced complexity version of this one. Soft minimal Okay. After that, we received whether these two proposed methods we will or not. Finally, we received the conclusion of this presentation. The basic problem inside engineering to recover the size of the length and observe the data from the vector B being of the length M and N M and N can be also called output data, which should be the length of the data, input data. The collection of this type of data based on the transfer function matrix A or the modeling matrix A. And A can be depend on each model, it can be chosen to the system designer. We have the input signal X, which is unknown, and we want to know vector X. It is passed onto the system transfer function matrix A, and it could be added by and it can be perturbed by the error or the noise due to the electric imperfection. And after that, we get the observation. But in this work, we will not consider the effect of the noise yet. If the noise is very low, we can approximate it as the total between matrix A, the transfer function, and the input signal. Conventional method to recover the X, which might be sparse, means that some elements in this vector may contain super seals. It is the method which is called linear least pair, or someone may call simply least pair. It's very well known and classical method. It can be used for both noisy case and noisy case. It is based on the L2 norm. The explicit solution could be expressed depending on whether M is less than N, or the length of the input signal equal to the length of the output signal, or the length of the input signal is greater than the output. In this case, we're going to consider the compression case or the underdeterminism, which is this one. M is less than N. And in this work, we propose two methods for sparse signal recovery. The proposed method make use of open roads inwards, and it is an iterative computational algorithm using the soft thresholding criteria. Previous work include L1R, which is criteria with L1 norm regularization. Another method related to this is L1 IRS. It is also a regulated criteria based on L1 norm. this work we consider the soft thresholding decision. The soft thresholding decision will be based on the size of the value of x in a certain value of threshold. And the size is the size of that number, for example, minus 1 would give negative and negative 1. Minus 7 would return minus 1 to us, or 0 if x is 0. And if x is 10, okay, we will get number 1. Okay, the pseudo LQ norm needs to be introduced because we use it as the way to count the number of non-zero elements in the vector x. And infinity norm of maximum value of the absolute of length in the x. Okay, soft homotopy is the method that use soft thresholding before, and it is the result of x plus gradient of this criteria, and then this is the soft thresholding, and the criteria make a decision based on the soft thresholding, the threshold value here, the lambda, and gamma will be the scaling factor, the shrinking factor, and we start from 0 as the initialization value. We have the soft thresholding value lambda 0 from these computations from infinity norm, and our method will be the same as soft homotopy algorithm, but we use the more Penrose inverse at this location instead of the typical A transpose. So we have additional A times A transpose inverse here. And the stopping criteria will be the same as this one, less than or equal to 2k. K is the number of non-zero elements in the x. Okay, but another one will be exactly the same as algorithm 2. In algorithm 3, we use only k without 2k. We will see the simulation result here. You can see that our method, the red one and the blue one, can provide lower Rubin relative error and respect to the number of non-zero elements. So if we have more data which are not zeros, we are going to have a little bit error like this. We compare it to the original soft homotopy algorithm. Here we get lower error. This is the typical criteria. And here is the L1 regularization. L1R, L1 is reference 14 and reference 15. Both of these are convex, and it can be computed by convex CVA eyes, which is available software. And here we plot it K, but we change the gamma, the shrinking value from 0.05 to 0.5. We can see that the error from the proposed method is lower than that. And here you can see the result. Once we use the gamma equal to 0.95, we still get lower error. And here the result from very tiny value parameter which changes to 20 and for the localization parameter. Okay, in this work we propose two methods that use inverse. The additional complexity would require only the inverse of these two metrics, and the multiplication first, and then inverse, and then the multiplication with A transpose. But it is computed only once, as we can see here. We compute only once, and here is the iteration. We compute it out of the iteration, so it's not computed every
updating. So the computational complexity is minor. It's not so much. The algorithm is improved for different values of shrinking parameters, and we found that the greater the shrinking parameter, the less the signal recovery. That's all for this presentation. Thank you very much.
Thank you. Do we have any questions?
So obviously,
and we're gonna move to the last paper in this session. It's entitled Hybrid RBFD and WLS Mesh-Free Strong Form Approximation Method. And it will be presented by Aditya Jankic from your Stefan Institute. Go ahead.
Okay, hi, welcome. My name is Mika with the Institute of Education from Slovenia, and I will be talking about a hybrid RBFFT and weighted least squares mesh-free method, mesh-free strong form approximation method. The outline of today's talk is something like this. So I will spend the first couple of minutes talking about the solution procedure when the system of partial differential equations is treated numerically. We will be using meshless methods, so a brief, really short introduction into meshless methods, because a couple of talks ago, Philip also already mentioned the meshless methods and explained them, so I'll be really short. Thank you, Philip. We will mainly focus on the radial basis function generated finite differences and weighted least squares approach. Then I will explain our problem, how we set the problem, and finally the results. So generally speaking, quite often in engineering and scientific problems are modeled with a system of partial differential equations, for example, a system like that one. And the issue with such systems is that they do not have a tractable solution. Obviously, we still need a solution. So what we do is we treat such systems numerically to obtain a numerical solution. And the solution procedure for numerical treatment of partial differential equations consists of 4 steps, let's say. The first step is we have to discretize the domain. Then we have to approximate the differential operators before we can discretize the partial differential equations. And finally, we assemble the things together to a large, sparse, linear system, which we solve to obtain a numerical solution. Generally speaking, of course, different methods have been proposed to treat the partial differential equation numerically. Generally speaking, we can divide the numerical method into mesh-based or mesh-free methods, where an important difference is that if we use the mesh-based methods, we discretize the domain by building a mesh. And if we use the mesh-free methods, we simply discretize the domain by positioning the nodes in the interior and on the boundary. Effectively that means that by using the mesh-free methods, no internodal connectivity information is required. So the meshless methods work on scattered nodes. Like I said, we will be using the mesh-free or meshless methods, and of course that means that also the approximation of the differential operator is a bit different, because in the context of
meshless methods, a differential operator L on U in some point x c is written as a sum of product between yet to be determined weights W and field values U. Now this sum runs over the sensor nodes, the support nodes, which are commonly simply the closest n nodes in the domain. Now the key point is how to determine these weights, which are computed by enforcing the equality of this equation for a given set of basis functions. As I already mentioned, we will be using the RBFFT variant of the meshless methods and the weighted least squares approach, where the RBFFT uses polyharmonic splines that are additionally augmented with monomials, while the weighted least squares approach uses only monomials as basis functions and Gaussian weights. We want to introduce a hybrid method, and the reason is that the RBFFT has been shown to be very stable, but it is computationally complex, while the weighted least squares approach is computationally cheap, but not always stable. So our idea is to take the advantages of the weighted least squares approach and combine them with the advantages of the RBFFT approach. And we do that by setting a problem, which is a simple Poisson problem with a exponentially strong source inside the domain. Here, for example, this problem also has a tractable solution, which allows us to evaluate the quality of the medicine. So we introduce the hybrid method by employing the RBFFT approximation in the neighborhood of the strong source. Why? Because we expect stability issues there. Everywhere. Elsewhere, the weighted least squares approach should be sufficient. And here are our results. These are convergence rates. The good results are the best seen for approximation order of 6, where the red line here, the red area, is the hybrid method, the blue line is the weighted least squares approach, and the green line, the green area, is the RBFFT approach. And what we see is that, yes, indeed, we were able to keep the stability of the RBFFT approach because, the weighted least squares is approach is obviously significantly more all over the place than the RBFFT or the hybrid. If we furthermore evaluate the spread, which was computed by discretizing the domain about 100 times, effectively resulting in approximately the same node count in the domain, just a bit slightly different position nodes. We can evaluate that by computing the difference between the maximum error and the minimum error, then divide that by the median error. And again, it is the most visible for the approximation order of 6, where we see that the red line is again completely covered by the RBFFT, the green line, which effectively means that, yes, we were able to preserve the stability of the RBFFT approach. And at the same time, if we take a look at the computational times, again, the green line is the RBFFT, the red line is the hybrid approach, our new hybrid approach, and the blue line is the weighted least squares approach. So not only were we able to preserve the stability of the RBFFT, we were also able to significantly reduce the computational times compared to the RBFFT. Of course, the method is more expensive than the pure weighted least squares approach, but it is more stable than the pure weighted least squares approach. As a final benchmark problem, we also solve a three-dimensional problem, which was a three-dimensional synesis problem described by the Navier-Cauchy equation. This problem, luckily, again, has a tractable solution. And yeah, the results we obtained are really good, quite honest. Yeah, because I mean, with the weighted least squares approach, we were unable to obtain a solution. So the weighted least squares approach is simply not stable enough to solve that problem. The RBFFD, on the other hand, is stable enough, but it took approximately 8 seconds. And our new hybrid method was again stable enough to solve that problem, and it took 30% less time. Which is, yeah, a good result. Oh yeah, by the way, we only needed to apply the RBFFD approximation method to about 35% of the nodes in the domain. The rest, so 65% of the nodes use the weighted least squares approach. Yeah, that's it. We introduced a novel RBFFD weighted least squares approach, where we observed good convergence behavior of the hybrid method. We were happy to see that we preserved the stability of the RBFFD method and the computational simplicity of the weighted least squares approach. The future work should definitely include error indicators to determine which nodes should use which nodes are critical for stability. And the RBFFD approximation should be applied while the weighted least squares approach is applied to the others. Because this was done a priori in our research, but that's not the best way. Thank you. Any questions? No. Error indicator indicates where the solution, where the numerical solution is not good. It's not good. Okay. So, all that it isn't the answer. I mean, the error indicator gives you a hint where you might have problems. And then you apply a more stable method there. Or no? The result was not enough. The result was not enough. Yeah. It doesn't converge to base zero. So it's not about accuracy. So it means okay, that's how we're going to determine that by its options. Yeah. Wait. Okay. And if I may, did you try here on this example? Did you try to find a threshold, like for hybrid method? Yes, for hybrid. No, I actually did. Yeah, so no, it was just the first setup. It worked, and you didn't bother to play with it. No, yeah, but effectively, what we can do is we would simply just more reduce the computational time. Because, but at some point you should maybe end up with divergent solution. Yeah, the transition from accurate stable. Yes, then we have a less accurate but still stable solution. Yeah, for 5 years. Actually, this was not the best display of the method because it also includes slow refinement. So the nodes in places where it's really not so difficult are already flat dense. So the actual improvement will be even larger if everything was the same.
Okay, if there are no other questions, thank you very much. And thank you everybody for participating. And I hope to see you again next year. So, well, in fact, probably
Da je nužno poznavati